This is the PCB version of the counting circuit, which counts from 0 to 9 forwards and backwards when the button is pressed. Let's take a look at the necessary stages for the creation of the counting circuit. This section of the NGO, or the NAND gate oscillator, is the analog input, and it's an pull-up configuration. When the button is pressed, there's a low and a low over here, as most of the current runs to ground, but when it's not pressed, most of the current goes here and becomes a high and a high instead of a low. So let's take a look at the NAND gate oscillator, one of the most important parts of the counting circuit. So when this momentary PBNO is pressed, there is a low and a low over here, which outputs a high. The high, then some of it goes through the diode and trickles down to the capacitor, and then the capacitor discharges into the 1 mega ohm resistor. And the high shows up over here, and the NAND gate acts as an inverter because it's a universal gate and becomes a low. The low and the low equal a high, and then the high charges the capacitor, and the high still goes through these two pins to output a low, which lights up the LED. Once the capacitor is done charging, it discharges through all of these paths. So this becomes a high, the high and the high still become a low, but this becomes a high. So this becomes a high as well, and the high and the low become a high, and the high, another high also drains from here, which becomes a high and a high, and is a low, which turns on the LED. Once the capacitor finishes discharging, this becomes over here a low. Then the high and the low become a high. Low comes from here, and this is high as a result of this. And the high and the low also become high, and then there's a low that comes from this. The low and the high become a high, which does not turn on the LED, turns it off because the two highs cancel out and there's no path to ground. Now these two RCs play a major role in the counting circuit. In the NAND gate oscillator, this plays the role of duration and how long it lasts, and the second RC plays a role in the frequency, and which is just how fast the LED oscillates. Now that we have an understanding of the NAND gate oscillator full circuit and how it works, let's see a demonstration of it. There's a new chip introduced in the decade counter, which is the 4017. The clock input comes from a pin 10 of the 4011, which is input into pin 14 of 4017, which is labeled clock input on the pinout of the diagram. The clock pin is responsible for the count to continue advancing. Every time the clock input becomes high on the rising edge, it goes up a count. Each output becomes a high as the counting progresses. The divide by 10 feature gives an output 1/10 of the frequency of the clock pulses by dividing the frequency that is inputted from pin 10 of the 4011 to the 4017 in order to slow it down and show the counting more clearly. The LED is on or high for the first 5 counts from 0 to 4, while it's off or low for the other 5 from 5 to 9. Next up, we have the decimal counting binary up-down counter, 4510. The difference between the 4510 and 4516 is that the 4510 can only count from 0 to 9, while the 4516 can count from 0 to 15. Counting is presented on binary on 4 yellow LEDs as seen. Binary counts from left to right, and depending on which chip is used, it'll count from 0 to 9 or 0 to 15. This is a crucial stage of the circuit as the binary is converted to a decimal digit in the next part. The binary counting decimal decoder uses the 4510 to decode the binary numbers provided by the 4510 or 4516 and presents it as a decimal number so that the human brain can understand. In the next stage, the 7 segments, which are part of the 7-segment display, are connected to the outputs of the 4511, which receives the binary numbers, converts them, and outputs them onto the 7-segment display as a decimal digit. For a normal function of the circuit, the store pin of the 4511 is usually low for normal operation. There was an addition of the switch connecting to the store pin. This can allow the freezing of the numbers that appear on the 7-segment display while continuing its count in the background on the 7-segment display. Specific parts of the 7-segment display light up as seen in the image here, if the number 2 was to be displayed, only segments A, B, D, and E are displayed on the display, and the others are off. This is the PCB version of the final breadboard prototype, and this is the PCB with the case. As seen, the previous circuits are crucial to develop an understanding of the counting circuit. Before you leave, think about the various applications of the logic chips and components in your day-to-day life, and I hope you have an understanding and a grasp on how the counting circuit works in general.